So we've reviewed reactions of benzene, and what we're going to do now is go into the reactions of substituted benzenes and some of their nomenclatures. There's a few things that we need to point out. The nomenclature is basically what you'd expect it to be. You take the benzene ring and you number the substituents so that you get the lowest possible numbers. If the name of the ring incorporates a functional group like sulfonate, for example, the substituent or that functional group is in the number 1 position. So if you'll look at the compound here on the left, what we know is that we have a chloro and a fluoro group. Because chloro comes before fluoro alphabetically, this would be the number 1 carbon and this would be the number 2 carbon. So there'd be a 1-chloro, 2-fluorobenzene. For the compound to the right of that, this is a sulfonate group. So this is benzene sulfonate. It's actually a sulfonic acid because it has a proton. And so this is a methyl group. So when we're doing the nomenclature of it, the substituent sulfonate becomes number 1, 2, 3, 4, and methyl gets number 4. So it would be 4-methyl benzene sulfonic acid. This would be the one on the bottom left. This would be 1 and 2, so that'd be 2-chloro. You'll notice that you have 3 substituents on this one, and so when you name it, the second substituent gets the lowest possible number. If you remember, that's how we did ties in straight chain molecules before. So what we'll do is we'll say, well, if I start on the fluorine, and that's here, call that the position number 1, and go here, that's 2, 3, and 4. If I start on chlorine, it would be 1, 2, 3, 4, 5. So now instead of being on the second substituent, in this particular instance, we're going to the third substituent in its numbers. So we're going to start with the 1 on the fluorine. So this would be 1-fluoro, 2-chloro, 4-iodo benzene. So if one substituent can be incorporated into a name, that name is used and the incorporated substituent is given the 1 position. So for example, a methyl group, that's this guy here, right, can be incorporated into the name as toluene. And so this would be 2-chlorotoluene or O-chlorotoluene. Systematically, you could also name it as 1-chloro-2-methyl benzene, because methyl benzene is also a systematic name for benzene. But typically, if you can incorporate one of the substituents into the name, the methyl, to make toluene, then that's how you'll do it. Now, the next molecule has an amino group and is a nitro group. If you can incorporate the name again, is what we're going to do here. We can incorporate the nitro group by calling this aniline, and so it becomes 4-nitroaniline. And then the hydroxy and the ethyl group, the hydroxy can be incorporated into the name as a phenyl group, or as phenol, and so we would call this 2-ethyl phenol. So just like how we've taken functional groups and incorporated it into the name of the compound for monosubstituted benzene rings, there are some disubstituted benzene rings that have also become part of the IUPAC, the systematic nomenclature. So a toluidine, that's this here, is like an aniline and a toluene, so it's become toluidine, and the O indicates that it's in the ortho position. Xylenes consist of benzene rings with two methyl groups on them. And so that would be M-xylene. And creosols are phenols with methyl groups on them. So what we're going to do next is look at a bunch of different types of reactions that can be um, done with alkyl substituted benzene rings, as well as nitro substituted. So there's actually a lot of reactions we'll be looking at for side chain reactions or substituent reactions. This is a listing of some of the ones that we'll look at for alkyl substituents. So one of the first things that we think about is radical substitution reactions when we think about benzene rings. And this is from the radical reactions chapter. If you use NBS, you get bromination at the benzylic position with NBS. NBS is N-bromosuccinimide. Uh, but once you've done that, then there's a whole bunch of other reactions that you can do. So for example, if you have toluene like this, and you react it with NBS, you'll end up with this bromo, so benzyl bromide, that's this guy here. And then once you've done that, this is just a sampling of reactions your book gives you. There's a number of modifications you can make to that to produce different kinds of functional groups. And just as a reminder, for things like nitriles, you can do reduction. So you can do like H2 reduction with a metal catalyst, and that'll make a CH2NH2. And you can also do hydrolysis with acid and water, and that gives you carboxylic acid functional groups like that. So there's actually a whole bunch of things that you could do to that. Oh, yeah, and besides H2, I should also point out you can also use lithium aluminum hydride for that. So there's actually a whole bunch of things that can be done at that point. When you do the substitution with an amine, one of the things the book points out here is that you need to neutralize that to get back to the amine. Otherwise, you have the ammonium ion. You can have both elimination and substitution if you have a good nucleophile, which is typically things that are weaker bases and the pKa's are typically less than 10, and you're not heating, so not strongly heating, I should say, because you do probably heat it sometimes. You can get a substitution reaction, but with bases that are moderately strong, their pKa's are relatively high, or they're bulky like DBN and DBU. They're not very good nucleophiles, or T-butoxide. Those kinds of bases typically lead to elimination products. So, let me get rid of some of these notes. I was just sketching some notes out here. I'll pause this for a second. Yeah, one of the things I thought it would be good to review is how you figure out what oxidation states are on carbon. So, in general, in organic chemistry, adding oxygen is oxidation. So, for example, if you take CH3 and you do CH4, and you do a combustion reaction on it, you'll get CO2 and water, right? This is a more oxidized state of carbon because it has more bonds to oxygen. But the other thing I wanted to point out is not just adding oxygen, but it's adding oxygen bonds to the carbon. So, for example, we'll start with, we'll call this first one A, we'll call this B, C, D, and E, so we can not just say that one and this one. So looking at A, the oxidation state of that carbon is -2. So how did I figure that out? Well, remember, hydrogen is less electronegative than carbon, and so in the compound at this carbon, this has a plus oxidation state and a plus oxidation state. That's the common oxidation state that you see for hydrogen. These are carbons, so they have no contribution to the oxidation state of the carbon that I marked in blue here. So overall, the oxidation state at this point here can be determined by, it's the charge of carbon plus 2 times the charge of hydrogen, which is plus 1, plus 2 times the charge of carbon of the oxygen, or sorry, the carbon, the contribution of the carbon, and that's equal to 0. Overall, that's equal to the formal charge at that carbon that I marked, so that's actually 0 as well. The result is that the oxidation state of carbon can be calculated as -2, which is what we got up here. Okay, so let's think about what happens with this carbon. I have one bond to oxygen and there's a hydrogen here, but there's one bond to the oxygen because the oxygen is more electronegative than the carbon. The oxygen will have a minus charge, the carbon will have a plus charge. So this is contributing minus overall, so that makes this plus, but this is plus, so that makes this minus. Now think about what that does. It cancels out. These two carbons don't contribute. The result is the oxidation state of that carbon is 0. Now, looking at C, this carbon has 2 bonds to oxygen. Each one of those removes an electron because the oxygen is more electronegative, removes an electron from the carbon. The 2 carbons on the left and the right have no contribution, and the result is this carbon is plus 2. So remember, if you're going up in oxidation number, this is oxidation. And if you go the other way, reduction is going the other way. Okay, so this going this way, this is reduction. So why don't you use that same rationale and try to do D and E. I'll pause the video and then I'll write the numbers above, so when you restart it, you'll be able to see that. Okay, so here they are. They're plus 3 and plus 4. So how did I get plus 3? I have 3 bonds to oxygen. Each one removes 1 electron or contributes plus 1 to that carbon. So that's why I get plus 3. And then for E, I have plus 4. I don't have a neutral carbon like I do on D. So I have carbon bonded to 2 oxygens, so that's plus 4. I also wanted to point out that's the highest oxidation state you can get for carbon, because once you've pulled the 4 electrons, you're down all the way down to the inner core electrons that you have to try to pull away, and those don't usually get pulled off too easily. And then the other way is that you're adding electrons. The most you can get is -4 for the oxidation state of carbon, and that's in methane. So carbon, right, with 4 bonds to hydrogen, each one contributes -1 basically to the carbon, because each hydrogen is +1. And so that's how I get this to be -4. So there's a couple of ways that we can do reduction of side chains. I put them up on this slide. These are from the textbook. Basically, you can use hydrogen and a metal catalyst to do a reduction. So H2, and then you'll notice like each one of these carbons picks up this. This is minus or plus 1. I'm sorry, -1. And this is -2 because it has 2 hydrogens on it. And so remember, going down in oxidation states is a reduction. So you can see adding hydrogens is a reduction of this reaction. And in this slide we use nickel, but we've often talked about using things like palladium and other metals to do reduction reactions. So for nitriles, we can do the same thing. Again, you can use lithium aluminum hydride for that. And then for aldehydes, there's a number of other ways to do it. But for metal catalysts, typically we're talking about nickel or palladium. As an important side note, benzene is so stable that it takes a high temperature and a high pressure, 180 atmospheres of hydrogen, in order to start the reduction of benzene. So you can do the reductions of these side chains with hydrogen and nickel at room temperature, at near atmospheric pressures, and still get efficient reduction of the side chains. You can also do reductions with hydrides. Sorry, I got to check my mic every once in a while. You can also do reductions with hydrides like lithium aluminum hydride. So for carboxylic acids or amides, lithium aluminum hydride will reduce that all the way down to an alcohol or an amine. And there's some other um, types of chemical reductions that we do. One is known as a Clemenson reduction. If you wanted to look that up, that's Clemenson. I think it's Let me see something really quick. Clemenson reduction. Yeah, I gotta sound it out and spell it out. And this bottom was known as a Wolff-Kishner reduction. And I'm not sure if it's a Wolff spelled that way. It might be FFE. Wolff-Kishner reduction. And the Clemenson reduction is done under fairly acidic conditions. The Wolff-Kishner reduction is done under fairly basic conditions, like either one of these is basic. Uh, and what they do is they result in the removing of the oxygen. And so you can take a ketone and reduce it down to a methylene group, a CH2 group. The other method that we talked about is called the Mozingo reduction, and that's using a thioacetal. So that's, for example, using SH2, CH2, CH2, SH2, and um, his second step is to use Raney nickel, uh, and that will also result in the same. The advantage of the Mozingo reduction is that it's done in relatively mild conditions. And remember, protecting groups can be affected by strongly acidic and sometimes strongly basic solutions. And so a Mozingo reduction gets away with not having to use those kinds of things. The oxidation of alkyl substituents is relatively straightforward. If you want to go to a carboxylic acid, you can use, for example, potassium permanganate, which is a strong oxidizing agent, or sodium dichromate, or chromic acid, for example, in heat. And what those result in is the formation of a carboxylic acid anywhere you have a CH type group attached. Now, that means if you have this group attached, it doesn't matter, or this group attached, it doesn't matter. All you get is this. So it cleaves everything off of the side chain and leaves you with a carboxylic acid. Now, if you wanted to form an aldehyde or a ketone, then what you have to do first, for example, well, let's say you just had this side chain. You'd first have to do a benzylic substitution with NBS so that you would have COH like this, and then CH2 and down to the benzene ring like that. And then what you could do at that point, so this would be NBS and then like OH minus or H2O, something like that. And you can get a OH group there, and then you can do an oxidation from there. But it turns out one of the limitations of these methods is that if you wanted to do the oxidation of something that looks like this, there's no hydrogens at this point, and the mechanism for this oxidation requires that there's a hydrogen there. And so you can do primary or secondary carbons oxidations using these methods, but you can't use a tertiary carbon. Now, if you have an alcohol and then you go ahead and use chromic acid, then you'll get the same result as if you hadn't had the alcohol there, and you'll end up with a carboxylic acid with the remaining carbons being cleaved off. Now you can form aldehydes and ketones by doing partial oxidations. One of the methods that we talked about previously is using ClO minus hypochlorite ion. We'll also do this, and you can also use PCC for the same reaction. Again, those are things we covered earlier. What those will both do with um, alcohols is convert them into ketones, or if you have primary alcohol, convert it into an aldehyde. Um, you can also you can also reduce nitro substituents using metal catalysts like palladium and hydrogen. You can also use a Clemmensen reduction we talked about before. That's the zinc earlier. It's the zinc and it had Hg after it. I don't know if I mentioned that part of it, but the Hg is mercury, and you dissolve the zinc into the mercury, and that allows it to react with the HCl and the nitro group. Um, so you can dissolve, uh, you can also use tin for that same reaction and form the protonated amine because under acidic conditions, because you need the hydrogen. This is also with HCl, Clemmensen reduction. You need the hydrogen to provide the hydrogen gas, basically, which is part of the reduction, or the hydrogen for the reduction to the NH3. But then it ends up being acidified, and then you have to make it neutral. This dissolving metal, this is another one of those dissolving metal reactions that we talked about before. You can also selectively just reduce one nitro group, turns out, uh, using this ammonium sulfide compound, and that will produce a single reduce a single nitro group to NH2. There are also some other interesting selective reactions that we need to sort of discuss, and so I'm just going to write them out here real quick. So, assuming you had this nitroacetophenone, that's what that would be called. This is without the nitro, it's just acetophenone. So it's M-nitro acetophenone, and you react with tin HCl. Turns out the product you get is this. So, so the ketone is unaffected, but the nitro group does roughly what you'd expect it to do from what we just discussed over here. Right? Over here up in this reaction that's up in here. Okay, so we do get that happening, but it turns out it doesn't react with the ketone. On the other hand, if you do sodium borohydride, what you end up with is you end up with this. You get the reduction to the alcohol of the carbonyl group. Why this exactly happens, I'm not sure is super clear, but the way that the tin reaction works is the nitro group comes into direct contact with the tin. The nitro has the two oxygens that are electron withdrawing on it. Remember, a nitro group looks like this. And so it's super electron deficient, and so it ends up needing an electron, and so it's easier in some ways for the tin to react with the nitro group. Now you would think that the borohydride would also react with it, but you have to remember, and this is kind of speculation on my part, the boron and the borohydride, there's a negative charge here, and it may be, and this is not clear why this happens, these negative charges keep them from interacting with each other. That is, it's too hard for the boron to transfer the hydrogen to the nitrogen to do the reduction of the nitro group. The result is then you can selectively reduce a ketone with borohydride in the presence of a nitro group, and you can selectively reduce the nitro group in the presence of a ketone using the dissolving tin HCl reaction. So in the first part of this lecture, we talked about electrophilic aromatic substitution reaction. So we had, for example, benzene, and we reacted with an electrophile, let's say it's Y+, and we substituted one of the hydrogens for this electrophile like this. So it turns out when you go to add the next substituent, the reactivity of benzene is very likely to be different than that of benzene, and that's because these substituents have electronic effects with the benzene ring. So there's two broad classification. They're activating and then there's deactivating substituents. And activating is essentially what it sounds like. If you replace the hydrogen with an activating substituent, the reaction of the subsequent electrophilic aromatic substitution reaction, the subsequent reaction will be faster. And in a deactivating situation, the subsequent electrophilic aromatic substitution reaction will be slower. Now, there's also a sort of a secondarily important point about these activating and deactivating substituents is they control where the next substituent ends up on the ring. Okay, so activating substituents increase electrophilic aromatic substitution, and deactivating decrease the electrophilic aromatic substitution of aromatic compounds. Now, if you're thinking about an electrophilic reaction, that is electrons leaving the ring and attacking the electrophile, the more electron density a ring has, the more quickly or the more activated it will be. So what activating substituents do is they increase the ring electron density either by induction, that is donating effects, or by direct electron donation. So inductively would be hyperconjugation, actually not by moving electrons, but by projecting electron density through the orbitals of bonds. And then the direct electron donation would be, for example, resonance with a lone pair of electrons being contributed by the substituent. Removing ring electron density is also done inductively by putting strong electronegative groups on the ring that create positive charge, or directly by resonance by pulling electron density out of the ring, i.e. moving the pi bond out of the ring. So here's the list of activating substituents from your book. I blew it up so you can see it. We have strongly activating substituents at the very top, and then we have weakly activating substituents at the bottom. And you'll notice that we have, for weakly activating, we have R groups like CH3, so alkyl groups, right? That's alkyl. And for the most strongly activating, we have, right, like amino groups, but all these have in common that there's a lone pair on the substituent. Now, nitrogen is not as electronegative as oxygen is, and as a result, nitrogen is a more strongly activating substituent, and oxygen is slightly less strongly activating. Now, there are moderately activating substituents, right? And the moderately activating substituents have a lone pair adjacent to the ring, but this lone pair has usually a group, like a carbonyl group adjacent to it, which then competes with in resonance with that nitrogen's ability to donate to the ring. So we have strongly activating lone pairs, no competition with resonance. We have moderately activating, which is a lone pair but some competition. And the most weakly activating are those things which have alkyl groups on them, or aryl groups like a benzene ring, for example, or alkenes. And primarily that's because fewer bonds to donate electrons through hyperconjugation. Now here's the deactivating substituents. The weakest deactivating substituents are fluorine, chlorine, bromine, and iodine, in that order. Now you would expect fluorine to be more deactivating than iodine, but again, it has a lone pair, and because of resonance, it can donate that lone pair more efficiently than the iodine can because of its orbital size. Fluorine's orbitals match with carbon's much better than iodine's do, and so while fluorine withdraws inductively, that is through the bond, inductive withdrawal because of its electronegativity, it donates back efficiently through its lone pair. So it is the least of the deactivating halides on the ring. And then we have carbons adjacent to the ring, which have double bonds attached to them. So we have partial positive charge here, so that's an inductive effect, but it also can pull electron density out through resonance. So, for example, if you have a benzene ring like this, and you have like that, then what can happen is this can go up, but that allows that bond to come out. And so it can withdraw by resonance. So we have moderately deactivating groups. If we add more oxygens or more electronegative groups to the carbon adjacent to the ring, it increases its electron withdrawing capability. And also, if you look at the strongly deactivating substituents, especially like the Nitro group, which is the most strongly, or these protonated amines, what they have on the ring is a positive charge adjacent to the ring. So I have a positive formal charge, like when you do a nitro group. The nitro group looks like this. I drew it earlier, but it looks like this. And that positive charge plus the electronegativity of the two oxygens makes it the most strongly deactivating substituent on the ring. So just a summary of activating and deactivating, right? All activating agents have electron pairs to donate, except for the weak activators, are ortho-para directors and are electron donors. And I guess we really haven't talked about that now that I think about it, but that's something we'll discuss shortly. And then deactivating substituents all have double bonds or positive charge next to the ring. The most strongly electron withdrawing groups are the ones with the positive charge. These all turn out to be meta-directors except for the halogens, which we'll see in the intermediates for the electrophilic aromatic substitution reactions can stabilize the intermediate with that pair of electrons that's on the halogen. So deactivating substituents lower the electron density on the ring, and they also destabilize any additions that are made in the ortho and para positions. So I've given an example here trying to put iodine in the ortho position puts a positive charge at this carbon, which delocalized by resonance puts the positive charge next to the electron withdrawing group. So in general, this type of situation is unstable, and as a result, the intermediate is higher in energy, and this particular product is slower to make. Now, if you do it in the meta position, and I'll draw that underneath. If we do the addition in the meta position, like this, zoom in just a little bit, then the positive charge is there. The nitro group is still here. I'm not going to draw the whole thing out. But the positive charge is there. These double bonds haven't shifted. And you'll notice what happens in the resonance structures. It avoids placing the positive charge next to the electron withdrawing group. So the result is there's less destabilization because of these particular resonance structures being a little bit more stable than when you put it in the ortho or in the para position. The para position would give you the same kind of interaction. And again, you can complete the reaction with the base, closing up, returning back to resonance. So these are resonance contributors. These ones are more stable than the ones that are shown above. Okay. Now, I did another thing to help summarize activating and deactivating. I drew some structures. So what we have is in the strongly activating contributors, we have lone pairs that donate. The moderately activating, we have a lone pair that can donate, but is also in competition with resonance in such a way that it doesn't donate electron density to the ring. And then we have the alkyl type substituents, or the aryl, the aromatic ring type substituents, alkenyl, the double bonded substituents, all operate through hyperconjugation. Um, Inductively, chlorine is a deactivating substituent, and then we have through resonance, and then we have with resonance and positive charge. So inductive and resonance effects. So I think this kind of chart generally helps to understand like what are the different contributing factors in determining how strongly activating or deactivating a substituent is. And those are the kinds of things for like a Chem 28B class I expect you to be able to look at a substituent and not necessarily have a list in front of you, but look at a substituent and determine whether or not it's more strongly activating or deactivating. I should point out, we've talked about this early on last semester. We talked about Chem 1B. Electron withdrawing groups in general tends to make acids stronger. We've never really talked about it too much in the context of aromatic rings, but it's still true with aromatic rings. And then if you look at electron donating groups, so those would be the alkyl substituents, for example. Those tend to make acids weaker because they make the substituent makes the ring more negatively charged, and as a result, um, tends to destabilize the anion, and as a result, it tends to make the acids weaker. The opposite is also true for bases. Bases are made weaker by electron withdrawing groups because the positive charge that's incorporated into the ring's resonance structures tends to stabilize the electrons on the substituent, like a nitrogen, for example, tends to draw them into the ring, and they're less available to be basic. It also turns out, because of some of the resonance structures that we drew before, substitution in the ortho and para positions tends to give different results than in the meta position. Here's an example. We have an electron, so we have a phenol basically, which is in creosol in this case, and this is an electron donating. This methyl is an electron donating group. The result is phenol, right, has a pKa of 9.8, but creosol has a slightly higher pKa. It's a slightly weaker acid. And that's because when you look at the resonance structures, the electrons are placed in a position adjacent to the electron donating group. On the other hand, when you look at creosol, its structure right here, right, M-creosol, when you look at the resonance structures for that particular substance, then what happens is when the electrons are donated into the ring, you'll have a negative charge here, here, and here. And the result is it bypasses this particular electron donating group. So they tend to be a slightly stronger. In fact, it's close. It's close to phenol as it is to creosol. It kind of splits the middle as it's in between the two. So I went and looked up a bunch of data. I don't think their book has these particular ones, but I went and looked up a bunch of data just so you could see some of the trends and how they're different. Again, ortho and para substituents tend to have larger effects in general than meta substituents. And so we're talking about chlorine being electron withdrawing. Just a side note, right? Phenol is 9.8 in general. In this particular study, when it was measured, it came out to be 9.9. So putting an electron withdrawing group tends to make it more acidic. For chlorine, it's a combination of both by resonance and by electronegativity. Turns out the trend is pretty straightforward. The closer it is, the stronger it is, and the further away it is, the weaker it is. For nitro groups, it's fairly distinct. If you'll notice, in the ortho and para positions, the acid is much stronger than if it's in the meta position, roughly a factor of 10 times. And then, but still, a nitro group on the ring, even if it's in the meta position, at pKa of 8.4 is still stronger than phenol, which is 9.9 in this study. But again, the ortho and para positions tend to be more pronounced for nitro groups. The effect that tends to be more pronounced, that is. So this is actually the second time I've recorded this section because, third time. One time my mic turned off, and the second time I forgot to hit record, and so I'm going to do this third time. I'll try not to go like horribly fast through it because it's a little bit frustrating to say the same thing like 3 times in a row. But anyways, let's look at A. When you do A, what's the problem, right? It's an alkylation reaction. In general, one of the things you'll need to know about alkylations is it tends to be messy. And so unless there's another way to do it, you tend not to do this pathway. Okay, so you'll get polyalkylation, and polyalkylation will primarily be this other product, the alkyl group being large enough and the substituent you're adding being large enough. Sterically, they probably want to stay away from each other, and so they tend to add opposite ends of the ring. Now, when you're doing thinking about other pathways, then you could either do the bromination first or you can do the acylation first. And I actually think that either one of these might be okay. There's one more step, and I'll talk about that because we really haven't discussed um, protecting groups on this kind of chemistry. But one of the things that you can do, for example, is you go from C, pathway C, you can do the acylation, then you can do the reduction. So that's the Wolff-Kishner or Clemenson or Mozingo reduction and form the propylbenzene. And once you have the propylbenzene, then it's a relatively easy thing to add the bromine in the ortho position. You just have to be aware that when you do something like that, what you're going to end up with also in your product is this. Right, so there's a mixture of products in that, and we'll talk about how you can resolve some of that as a problem. Now, you can also do it with F. F, you do the bromination first, and then you do G, you do the acylation, and then you do the reduction of the side group to form the desired product. But again, you sort of had that same issue. Typically, you could do either, but typically what you would normally do actually in the step, and it's not shown in here, is you'd add a protecting group. So for example, I have this acyl, this bromo group here, right? Or I have this alkyl group here. The in-between step would be to add a sulfonate group. So for example, for this product, let's take this one here, right? What I would do first is I would add a sulfonate to it. So that was fuming sulfuric acid, so it would be HSO3 like that. And that would probably go predominantly in the para position because the size of the groups is big enough probably to cause it to go para. And then you could do bromination. Now, sulfonate is a meta director. This is an ortho para-director, and what you'll end up with is you notice they're both directing to this position here or this position here, either one. You'll get a bromine here and an alkyl group here, and then the sulfonate over here, aromatic of course, and then you can do the removal to get to the final product, the desired product. Okay, and remember, to do the sulfonation, that was concentrated sulfuric acid heated, and the desulfonation is just using H plus dilute and heating it, and that'll remove that sulfonate group in the para position. Now, if you do the same thing with the bromine's much smaller than the alkyl group, and you'll probably not get as much of the sulfonate in the para position, but I kind of think both of them will work okay. Like, both of them are reasonably acceptable. The only modification to either of the ones shown is to add that sulfonate group in the para position and then remove it later to increase your product yield. Okay, let's look at M-nitro benzoic acid and its synthesis test. So, how do you make M-nitro benzoic acid from benzene, right? So, we have to think about this. Both are meta-directors. So, from this perspective, it's possible that in retrosynthetic analysis, the precursor could have been either of these. That is, I could have a nitro group, say NO2, or I could have had a carboxylic acid like this, right? So we could have had that first. So both are meta-directors. Both would give us the suitable product if you can add them. The question is, you know you can add a nitro group, but how do you get this group on, right? And it turns out there's not a good way to put a carboxylic acid directly on the ring following nitration. Remember, in order to get the carboxylic acid, you're going to have to do like a Friedel-Crafts acylation or alkylation reaction, and those won't happen under the conditions when there's a nitro on the ring. So we have the nitro on the ring that's more strongly deactivating, which means we have to go through the acylation / alkylation route first. So again, that means going this route synthetically. So now what I have to have at this point, oops, that's weird. Okay. You have to have this or this. Now, problem is this gives us bad yield, and this is not easy to oxidize, and so there actually has to be a step. Remember, we talked about in the oxidation of a benzylic carbon, that benzylic carbon has to have a hydrogen on it in order to be oxidized. So actually what has to happen, and this may sound weird, what has to happen before you get to this point here with the oxidation is you're going to have to reduce it down to like an alkane, so, or an alkane side chain. So in other words, we're going to start with the product, thinking about our product like this. And then I'm say COOH. Backing it up, we can make this, oh, I should go this way, sorry. Retrosynthetically, I got to back this thing out to this. This part's okay. But then I have to think about how I'm going to make this, and that needs to come from something like this, okay? So how do we get to that? Well, that we get to from this. So we're going to have to do an acylation. Oh, sorry, I can move this slide. I'm going to have to do the acylation and then do the reduction to the alkyl substituent, then the oxidation to the carboxylic acid, and then to the product. So before this is benzene. So those are the steps that'll be involved in that particular synthesis, unless I'm missing something, and I'm pretty sure I'm not. This step that I'm showing here, going from this like that, retrosynthetically, is not easily accomplished, except for you might be able to use, I think there's a reaction with NBS that can do that, but it's not one that I've looked at in a long time. So to be honest with you, I don't see a clear-cut like way to do that step. So the thing that you will end up doing is in the forward direction. Okay, so we're going to do that here. Going to start with benzene. We're going to do the Friedel-Crafts acylation, and you'll fill in the reagents there. And then we'll do the reduction. And then we'll do the oxidation to the carboxylic acid. And that's a meta director, so then we can just do nitration. And I've drawn this a little funky. It's just not the way it was on the screen, but remember it was meta, so that we can nitrate the meta position like that. And that should give us a reasonably good product yield. The only trick is there's a lot of steps involved, and so I'm not sure you can avoid that. You have to do that acylation, reduction, and then oxidation, and then the nitration. All right, so let's look at tri-substitute products, and I try to do one or two examples of this as well, but in lecture it's kind of in person. It's a little bit easier to work some of this out when you guys ask questions. But here is what you have to think about when you have three substituents. You have to think about whether or not the first two substituents that you add will work together to give you a particular product, right? And substituents will generally compete with each other for ortho, para / meta for the third substituent. So, for example, let's look at, I have an ortho para director here and a meta director here. Those are working against each other. Ortho para would be to that substituent would be here, and then meta would be here. And so if the red hydrogen is the one you want to replace, what you have to make sure of is that the meta is a stronger meta director. Then what you'll get is primarily substitution in the meta position, but if the ortho para director is stronger, you'll get ortho para substitution. So you have to think about the relative strengths of the directing groups when you're doing this kind of analysis. Now, it could be happy day, right, that they work together. So if you have a meta director and a meta director and you're trying to replace this hydrogen, then it's relatively easy. They both work to substitute the same position. Now, you could also have the same thing with ortho para directors. So now notice you have two ortho para directors. They're actually meta to each other. But when that's the case, I have ortho, right? This is ortho. And this is para, of course. But then here, that's para. But you notice that's also ortho to this one. So they're both working to do substitution in the same position. Now, notice this is ortho to both of them, and if the substituents aren't large, that's generally where the substitution will be. But because of there's a lot of steric crowding in the space between the ortho para directors, oftentimes it'll be outside of that carbon. Now, what about this last one? I have an ortho para director and a meta director, right, adjacent to each other. Now, if you're thinking about this, right, where does the substitution take place? Well, meta is here, and para is also at the same position. So that's para, that's meta. And this one is ortho, and you'll notice going in this direction, that's meta. So they're working together to put the substituents. Now, if the substituent is large, it'll probably be here. And if a substituent is small, then it'll probably be there. But the ortho pair and the meta directors are working for the same position. So then if that's what you wanted to do, then you have to think about what's the order of adding these two, right? So like before you made that, then what you had to have is you had to have the ortho para director here so that the meta director would be added to this position here. And then that tells you the sequence of reactions that you need to have in order to get that third substituent on. So I made this example up so we have something a little more concrete to look at. So first thing that I'm looking at when I look at these substituents is I just, at face value, I say, well, this is orthopara directing. This is meta directing. This is meta directing. So when I look at it in that perspective, not thinking about what the substituents are, but what their function is in terms of electrophilic aromatic substitution reactions, bromine had to be put on last. Bromine had to be put on last because if it was put on earlier at some point, then you would expect one of the substituents to be ortho or para to the bromine, and both of them are meta. So prior to this step, the bromination happened last. So retrosynthetically, I had this. And now, cool, right? The problem is, what was the order? Because these are both meta. What order would you have done? And so you have to think about some of the reactivities of these different kinds of substituents. Now, nitro can be added at any point, but an acyl group, a carbonyl like this, can only be added if there isn't a strong deactivating substituent on the ring already. So what that means is, retrosynthetically, I have to have added the nitro group before the acyl group. I mean, after the acyl group, sorry. So that would have been my product or my reactant immediately preceding, because the reaction going the other way, the acylation can't be done with the nitro on the ring. And then this leads us to benzene like that. Okay, so those are kind of some of the considerations. You could fill in the reactions that you would have in order to do a substituent, or product with 3 substituents on it. So diazonium salts are an important class of compounds for organic synthesis. We would have in a normal semester made a diazonium salt and then made a diazonium dye and used that for tie-dyeing lab coats and stuff. I'm hoping that we can get back to that point later this semester when we return, if we return. But right now it's kind of looking like that's not going to happen. So let's go ahead and go over the diazonium salt. So starting with a nitro group, you reduce it into an amine. So that gives us, this is aniline in this case. And then 0 degrees Celsius. So basically it's in ice. It's aqueous with ice. And you add sodium nitrite. Now sodium nitrite is that thing that they add to pork actually to give it the red color. You can actually, you used to be able to just buy it. I don't know if you can anymore. Right at the grocery store, and then make bacon and stuff like that. It's the redness in the bacon is caused by nitrites. But then the sodium nitrite and HCl are added together, and it makes this diazonium salt. So this is the diazonium salt. It can be it's relatively easy to take the diazonium salt and reduce off the nitrogens as nitrogen gas. That's N2. You can use sodium hypophosphate, or phosphite, sorry, or sodium borohydride to do that reaction. It also has some other interesting features. You can imagine that the diazonium part, the nitrogen that's here, is a great leaving group as well. So there's a number of reactions that diazonium salts are involved in because the nitrogen is such a really good leaving group. Of course, the one I just mentioned is you can just reduce it off directly with sodium hypophosphite, or sorry, I said sodium hypophosphite before, hypophosphorus acid. I think I'm just getting tired. I can only do these lectures right now. It's about uh, 3 in the morning, I think. Yeah, 3:20, because my house is so busy and my wife is doing stuff with lectures and online stuff all day long. So basically working through the night so I can get up in the morning and put all this together for you guys and post it. Anyways, if you take a diazonium salt and you add just a slightly acidified water to it, you can form a phenol. In fact, this is one of the only ways that we can get directly onto a ring in OH group. Sodium borofluoride can also be used to substitute. The fluorine adds just like a hydrogen does. Um, with copper chloride, you can chlorinate the ring, so chlorobenzene, and then copper bromide salts as well. And Ki can also be used. And you can add cyanide using these cuprous salts as well. Now, these copper salts are part of a reaction family known as Sandemeyer reactions, which I think I have down later, but those are Sandemeyer reactions. So, these reactions, these are substitution reactions, but it turns out that they're or instead of being electrophilic substitution, they're nucleophilic substitutions. And what the diazonium portion of the benzene ring does is a strong, strong electron withdrawing group and tends to make it so that a nucleophile can come in and substitute it directly off the ring. So in general, just a sort of side note here, right? Hang on, let me change my marker. Uh, the nucleophile can come in directly and do a substitution reaction. Now, the Sandemeyer reactions, similar types of reactions. These are copper 1 salts. So these are Cu plus Br minus copper 1 plus salts. Can also be used in these reactions, and you can get a direct substitution of the diazonium portion with the halogen. Now, diazonium salts are good leaving groups, and typically the pattern is something like this. If you want to do orthopair substitution, so you want, for example, this substitution pattern. If you think about what was there right before, because you notice bromines are all meta to each other. The way this is done is by having an amine present prior to that step, and then adding the bromines. Now, the aniline that you start with is active enough. You can do the bromination without a catalyst, and you add the bromines in ortho and para to that group, and then you use a diazonium salt to replace that with a hydrogen or some other functional group. Here's another example. Here, right? How did you make that, right? Some things that only diazonium salts can do easily, and this is one of them, again. First thing is you have to recognize that the chlorines are meta to the OH group, but OH is an orthopair director. So what that means is that the OH must have been something else. It must have been a meta director. And that's the kind of thing that you have to think about when you're dealing with like the diazonium salt reactions. Is you have these substituents, they're in a position that's impossible for the current substituent, so you have to think about like what did I use to replace that. So for example, right prior to this, you had to think that at some point there had to have been a meta director there, so like an NO2. And NO2 can be removed just like NH3, but NO2 makes sense because the chlorination would be meta to that. So prior to that, I would have had a nitrobenzene like this. And then prior to that, I could have had just benzene. Okay? So it's important to think about these transformations when you're doing that. So let's look at these two sort of in more detail. A lot of steps involved. This is the starting point. Let's start with the nitration, which is A, right? And then we do the reduction to NH2. So that's a Clemenson or tin HCl type reaction. Clemenson's, remember, the mercury zinc reaction with HCl. And then you can do directly, you can do the bromination. So this step is just Br2. So I'll just write that down. That's the only one that's really significantly different than we've looked at before because the amine group is a strongly activating group. And then what you do is you convert it to the diazonium salt, and then you use the H2PO to the hypophosphorous acid, then to reduce that off. Now, if you see something like this and it has an OH group, it could have been an OH group, and then, right, you could have done the diazonium salt to put the OH group on there as well. All right. This is the one that we were talking about before. I have a benzene ring. I need to have an OH group with the Cl groups adjacent in the meta position, right? Step before that, though, have to go through the diazonium salt. That means it had to be the amine, which is a reduction, again, a Clemenson type reduction. And then you end up, can be at a nitro group, and so you have nitration. So A is a nitration, B is a halogenation, and because nitros are meta-directing, you'll have the chlorines meta to the nitro group. Then a reduction using like tin HCl, and then uh, conversion to a diazonium salt, and then finally replacement. Remember, this one is just H2O and H plus. It's a hydronium ion. So basically, you get a nucleophilic addition of the water and replacement of the diazonium salt. Okay, so again, all these reagents are ones that you can easily look up in the slides. So I'm not going to repeat them. All right. So I mentioned earlier that we were planning on making diazonium uh, dyes. So they're called azo dyes, and using diazonium salts to produce them. And it turns out the mechanism for that reaction is shown here. You have a phenol which would attack this particular nitrogen, and the electron pair would go back to there. And then again, you would have a carbocation, an aromatic, that would then eliminate to give you the aromatic ring back. So it's an electrophilic aromatic substitution reaction. And so you end up with this what's called an azo linkage, and these nitrogens would, both have lone pairs on them like that. So it's done in this particular instance in the pair position because the hydroxy group of the phenol is a strong ortho pair director, and then the electrophile is relatively large, and so it tends to go in the pair position. If you have methylphenol, what happens is both of them are ortho para directors, but they're in each other's para position. So the major product is the one that is directed by the more strong ortho para director, and so that's the phenol. And so the electrons go like that. You get a lone pair on that nitrogen. That's a two-headed arrow if you can't see it. Again, there's a pair of electrons here and a pair of electrons there. And that's the product that you would get. Now, the formation of the diazonium salt is actually shown on these next two slides, and I would like you to know what that reaction is. It's actually really similar to the nitration and sulfonation reactions in that you use an acid to protonate one end of the nitrous acid. In this case, it's hydrochloric acid, and then that group leaves and gives you this nitrosonium ion. The nitrosonium ion is a fairly strong electrophile, and it is attacked by the lone pair on another nitrogen. And then by process of elimination, you'll notice like this is an acid-base reaction here. This pair of electrons can then cause this oxygen to pick up another hydrogen. And that process, again, through another acid-base reaction, repeats itself. So the same thing happens a couple of times, and that's what creates the triple bond between the two nitrogens eventually. So the last important class of reactions are known as nucleophilic aromatic substitution reactions, or SNAR, or SNAR reactions. So in a SNAR reaction, what you have to have is two strongly deactivating substituents on the ring. These substituents pull enough electron density out that a nucleophile can get past the pi electron cloud of the benzene ring and do a nucleophilic attack. And then again, because the aromatic product is so much more stable, we get a substitution rather than an addition reaction. So to give you an idea about how this depends on the electron withdrawing groups, you can run this substitution reaction at pH 14, which means basically it's 1 molar sodium hydroxide and it's 160 degrees Celsius. You have an electron withdrawing group here. The hydroxide is your nucleophile. Remember, this is substitution nucleophilic aromatic. The OH group comes in here like this and forms an intermediate, which then when the base comes and removes a proton, kicks the chlorine off and leaves the OH group behind because the OH is the stronger base of the two. Now, if you add two electron withdrawing groups, and notice the relative position, right? The NO2 groups are orthopara to the group to be substituted, the leaving group. If you have two strong electron withdrawing groups, the electron density is low enough on the leaving group site that you can run this thing at pH 10. Now think about what that means. That's 4 orders of magnitude lower concentration and a lower temperature as well, and get a reasonable reaction rate to come out of this thing. And then if you look at it one more time, right, you add one more nitro group. Again, these groups are orthopara to the chlorine substituent. Remember, nitro groups increase the partial positive charge at this carbon by withdrawing electrons from the ring in the ortho and para position. All of those nitro groups on a relative position are ortho or para to that leaving group. This reaction can be run at 40 degrees Celsius and at pH 7, so 7 orders of magnitude. So it's relatively easy to get this nucleophilic substitution reaction to occur when you have 3 strong electron withdrawing groups on it. Again, the mechanism is shown here. The nucleophile is attacking the carbon with the leaving group. Then we have a number of resonance contributors which stabilizes the intermediate. These two in particular are additional resonance structures because of the nitro group. And then you have the elimination to produce a substitution. So remember, we have nucleophilic addition attack, which is like an addition, and then we get the elimination of that group at the end, and the group that's the better leaving group is the one that leaves. This set of intermediates, which you should be able to draw for a reaction, are known as the Meisenheimer complex, which is that series of 4 resonance structures that explain the ability of this reaction to take place. Another reaction that you need to be aware of is the formation of benzene in the presence of a very strong base and a leaving group. Okay, so you have a leaving group on the ring, that's this, and you have a very strong base like amide. Remember the pK of that's like 36 for ammonia. And you can actually form this triple bond. And the triple bond is very reactive, and you can add another substituent to it because of its reactivity. So it's a direct addition if it adds to the carbon. That's the red arrow. Notice this is red and this is red here. The red arrow is known as a direct addition, and then you can have the sign addition when it attaches to the adjacent carbon. And then you can get an aniline out as a product. Now, the way they know this is the mechanism for the reaction is they actually take a benzene ring with the carbon with the leaving group labeled as carbon 13 or carbon 14, and then they can do a spectral analysis to determine which carbon the chlorine is attached to, or that a nitrogen is attached to at the end of the reaction. And as it turns out, you get an even proportion of the nitrogen either directly substituted or on the adjacent carbon. So benzenes are really reactive. One of the things you need to know about benzene is you get super poor overlap. Remember, in a standard pi bond, it's side by side, but in the benzene ring, that triple bond, remember, one of the bonds is top and bottom going through the benzene ring. The other one has to be in the plane of the molecule. That's this one here. And because these orbitals are pointed outwards from each other, the overlap is very poor, and that's one of the things that leads to benzene being very reactive. Lastly, we're going to talk about naphthalene and some of its reactions. It's a little bit more reactive than benzene because it's kind of got a built-in electron donating substituent. It turns out position 1 is the faster of the two substituents because of the intermediate, but substituent number 2, it placed at the number 2 position, tends to be the thermodynamic because it's further away from the other ring. That is, in particular, it's further away from this hydrogen here. Okay? All right. So let's say you put an activating substituent on a ring. The second substituent will tend to go on the same ring. If you put a deactivating substituent on the ring, then what tends to happen is the substituent gets added. Second substituent will get added to the second ring, okay, the other ring. The same rules apply if you have an activating substituent, then the next substituent tends to go ortho and para to the activating group. And if you have a deactivating substituent, then what ends up happening is it tends to go in the kinetic position of the other ring. So for example, let's say I take a naphthalene like this, and I put an activating substituent here. Yeah, that's okay, that's fine. Then the next substituents would go here or here and not on the other ring, because what the oxygen does is donate electron density to the ring, and it tends to more activate the ring it's attached to than the ring that's next to it. Now, if you add a deactivating substituent, let's say like a nitro group. Let's do NO2 here. Then what happens is this the ring that it's attached to is more strongly deactivated, which means the other ring is going to be more active. It tends to add into the kinetic position, the faster of the two positions, because of the stabilities of the carbocations that are created. An interesting thing that you can do is if you run the reaction so that you get the kinetic product, which tends to be the lower temperature reaction, you tend to get addition to the 1 position. You can take that same product and heat it, and it'll convert over to the thermodynamic position, which is in the 2 position here. That group can leave and reattach in the thermodynamic position. Okay, so um, the reason that's the thermodynamic position, again, as I mentioned, is that there's a hydrogen here that tends to push it away, and that allows the group on the number 2 carbon to be more stable than on the number 1 carbon. The intermediates are interesting to look at for their stability. And so what I've done is I've pre-drawn these because it takes a while to draw them all. Let's say you get an addition. Remember, this is the number 1 position. This is the number 2 position. So what ends up happening when you add to the 1 position is you get a carbocation at the 2 position, and then you can draw a number of different resonance structures. There's actually 7 of them, and you can sort of follow along with the arrows that are given. But of the 7, 4 are aromatic, right? And that aromaticity of the resonance structures causes them to be much more stable, and that leads that to being the kinetic product. To compare, I did what would happen if you add it in the number 2 position. So remember, this is the 1, and that's the 2, right? So to the number 2 position, there's a number of different resonance structures. The blue arrow, if that arrow happens, that's this transition here. This is the intermediate that you get. That is an aromatic ring. Now, if you draw all the other resonance structures, eventually you get to this one, and that has also got an aromatic ring to it. When you count them up in total, there's only 6, and only 2 of them have aromatic rings. And so the result is that particular intermediate ends up being less stable than if it's added in the 1 position. Now, intermediate stability leads to kinetic product, right? And then structural stability lends to the thermodynamic product. So what we've just been talking about when we're talking about carbocation stability is intermediate stability. The 2 position, the intermediate, is higher in energy because there's few aromatic resonance structures, and there's only 6 resonance structures in total. Now, again, when you're looking at, going back up here, all right, the summary, the kinetic is addition into the 1 position. The thermodynamic is the addition into the 2 position. If you have a substituent on the ring, right, then you have to think about for the second substituent whether or not that first substituent is activating or deactivating. So here's an example of a deactivating substituent. Right, remember that slows the overall reaction down. On the ring it's attached to, this ring reacts slower. And as a result, it'll add to the other ring, but in the position which is kinetic, that is the faster of the 2 positions. If, on the other hand, it's an activating group, like a methoxy group, you can do the acylation reaction, for example. The acylation reaction happens on the ring in which the activating group is present. And that substituent adds ortho or para to that substituent. Okay, so here's another 2 examples. That one's ortho para, so ortho is here. Para is occupied, right? So you can add to that position or that position, and it turns out it'll add to the 1 position because that is the kinetic position. So what happens with these? There's some practice problems for um, polycyclic aromatic systems, right? Where does the substituent most likely add? So why don't you go ahead? I'm going to pause the video. You pause the video, and then I'm going to write the answers in, and you can see if what you get jives with what I come up with an answer for. So here's the answer to the first one, and the reason I put it on the ring to the left is because this oxygen has lone pairs to it. It's electron donating to the ring to the left. This is withdrawing electrons, and so it deactivates the ring on the right. So the left ring is activated, the right ring is deactivated. It's an ortho-para director when connected in the fashion with the oxygen to the ring, and so the bromine ends up being para to the oxygen. So go ahead and pause again and give this one a shot. So that's what I came up with. Phenyl groups are activating substituents. You can do ortho or para. I assume because the phenyl group is large, the para product would be higher in concentration in the final product, but you could also have a significant amount of that, like that, okay? And finally, there's these three products. And what I'd like you to do is try to figure out how each could be made from benzene, and then we can talk about it in office hours this week when after you've watched this entire video. And then remember, we have online office hours during our class time, and also GRASP on Friday to sort of go over some of these kinds of questions that are in the lectures. Okay, so go ahead and try to do these. You can discuss amongst each other, for example, and then see what you come up with for office hours.